Okay, this is the notes for section 4.2, reflecting figures. If you haven't done so already, make sure you pause the video and read 4.2 before going on. The first thing I'd like to look at is the reflection postulate. It's a fairly important postulate as we look at this entire chapter, as we deal with different reflections and how we can put reflections together. So there's different parts to this postulate, and I just want to go through each of those for you and kind of talk about what's going on there. So if I have an example of a reflection over here. So as I'm going through this, we'll be referring to this picture to help us kind of better talk about each of these properties. The first is that there's a one-to-one correspondence between points and their images. What that means is that for every point that's on my pre-image, A, B, C, D, there will be an equivalent point on the image A prime, B prime, C prime, D prime. Okay, so we're not just talking about the points that we have labeled on each of those image and pre-image point, but also any point. So if I have a point right on this line segment, there's another point on the line segment over here that is the image of it. Okay, that's what a one-to-one correspondence means. Part B is that collinearity is preserved. Now we got to think about that term, collinearity. Remember, collinearity means that points that are on the same line. So when we say collinearity is preserved, what we're saying is that points that are on the same line in the pre-image will also be on the same line in the image. So you'll notice that A, B, and C, all three of those points are on the same line, just like the points A prime, B prime, C prime are all on the same line over here. Collinearity is preserved. Okay, I'm going to underline here the C, because I'm going to come back to that in just a little bit. The next part is betweenness is preserved. Betweenness, remember when we say a point is between two other points, it means that a point is on a line segment between two other points. So what that is saying is that if betweenness is preserved, is that if a point is between two other points in the image or in the pre-image, it will also be there on the image. So we'll notice that B is on the line segment AC and between A and C. B prime is also on the line segment A prime, C prime, and between A prime and C prime. So that will always occur when we do reflections. I'm going to underline the B from that one. Okay. Part D is the distance. Distance is preserved. Okay, and what that's telling us is that between A and D, that distance will be exactly the same as the distance between A prime and D prime. Okay, so when we say distance is preserved, what we're saying is that something like AD, it will always be equal to A prime D prime. Okay, and I'm going to underline the D for that one. And then for part E, we have angle measures preserved. Okay, and angle measures preserved is saying that once I reflect in a pre-image to get an image, that angles will remain the same measure. So if I look at this angle right here, angle ABD, that will be exactly the same as the angle, angle BAD will have the exact same measure as B prime, A prime, D prime. Okay. So I'm going to underline the A. Now, those four parts of the reflection postulate are the things that are preserved in all reflections. And the way that we can remember that is A, B, C, D. These letters that I have underlined. So A is for angle measure, B for betweenness, C for collinearity, and D for distance. Those four things are preserved in all reflections. Okay. The last thing that we're looking at is orientation. And orientation is reversed. Now when we talk about orientation is either a clockwise or counterclockwise. So if I'm reading the points of a figure and I read them around, so for instance, if I'm looking at my pre-image here, A, B, C, D, I'm reading them around in a clockwise manner. Okay. Well, when I say orientation is reversed, that means that when I read the image points around in the same order, A prime, B prime, C prime, D prime, you'll notice that I'm going counterclockwise, so that image is reversed. Okay, the next theorem is one that I actually already applied in 4.1 when I showed you how to do reflections over lines, but I want to kind of go through it here a little bit. It just says a figure transformation theorem just says that if a figure is determined by certain points, then its transformation image is the corresponding figure determined by the transformation image of those points. So really what that theorem is telling us is if I'm going to perform a reflection, I don't have to reflect every point of the figure, because if you look at a figure, so for instance as I look at this drawing right here, this figure A, B, C, D, E, F, there are an infinite number of points on that figure. So I can't really reflect each one of those individually because there's an infinite number of them. This figure transformation theorem is saying, hey, if I reflect those vertex points, since the vertex points determine what that figure looks like, then I can reconnect those to make my image. Okay, so it's just telling us that if we're performing reflections, all we need to do is reflect those vertex points. Now, it's also going to, when we get into proofs, it's going to be something that we're going to use to show that if I know that each of the points that make up a figure has been reflected, then I know the entire figure can be reflected as well. So for example 1, let's use our figure transformation theorem to do this problem. So if I want to reflect PQRST V over line N, what I'm going to do is I'm going to just reflect those vertex points PQRST and V. Once I get those points, then I can reconnect those points and I'll have my final image. So if you remember, we did in 4.1, we're going to bring our ruler over to one of the points. Now P is on the line of reflection, so that one's not going to move, so we can actually leave that one alone and assign it P prime as well. But I'm going to do each of these other ones by the same method. So I'm going to move my ruler over so it's at a perpendicular to the line, 90 degrees, and then measure the distance from that point to the line, and then the same distance on the other side of the line for the new point. So as you can see, I've got R lined up here. I've got my 90 degrees on the line. It looks like just over 1/10 of an inch. So I'm going to do the same thing up here to put my new R point. Okay, then I'm going to repeat the process with each of the other points to come up with my final figure. At this time, why don't you do the same with this figure, reflect it, and I'm going to put the answer up. Alright, so here is the answer then to example 1. You'll notice that I've reflected each of those points. Okay, and then once I've reflected them, once I have those points done and taken care of, then I'm going to connect them. I have them as a dotted line. You don't have to do that. You could do it as a solid line as well. But I've reconnected those points to get my final figure there. Okay, so let's take a look at example 2 here. It says give the orientation of PQRSTV and then give the orientation of the image of that. So if I look at this figure here, if I'm starting at P and going around, you'll notice that I'm going around in a counterclockwise direction. Okay, and if I look at the image point, I'm going around in a clockwise direction. So orientation has been reversed. So the answer there would be that the pre-image point is counterclockwise and the image point is clockwise. Okay, let's take a look at example 3. In example 3, what we're doing is we're trying to apply the reflection postulate, all the different parts of the reflection postulate, to the following reflection. If I do a reflection of triangle RMG over line GN, so here's my line of reflection right here, GN. Here's the figure that I'm reflecting, RMG. Okay. Now, some things that we have to recognize is that when I do that and I write it like that, that R, the reflection image of R, is B. The reflection image of M is P, and the reflection image of G is G. So wherever they are in order in terms of how we write it, the corresponding one will be in the same position when we write it for the image as well. Okay? So let's take a look at this. Part A says the measure of angle P will be equal to the measure of what angle? Well, the reflection image of angle P would have to be angle M. Therefore, the answer to that would be angle M. And the reason for that is because we know that reflection preserves angle measure. Okay? Part B, I'm saying the distance from R to M. That's what that represents, the distance from R to M. What would that be equal to? Well, if I reflect RM, RM is the first two over here, therefore it's the first two over here as well, BP. So the reflection of RM is BP, therefore they have to have the same length because reflection preserves distance. So the answer would be BP here because reflection preserves distance. Okay. Part C says that RB is 18, RO is what? Okay, well, RB is the distance from a pre-image point to its image point. Well, I know from the definition of reflection that the line of reflection has to be the perpendicular bisector of that segment. Okay, and perpendicular bisector means it divides that segment into two equal segments. Therefore, if RB is 18, RO has to be half of it, or 9 units. Okay? And the reason for that is because we know that the line is the perpendicular bisector of RB. Okay? And then part D says angle GOR is going to be what measure? Well, that would be 90 degrees. Okay? Because it's going to be the perpendicular bisector of RB. Okay, the last example I'd like to look at is number 4 here. It says let EFGH equal the reflection over the x-axis of ABCD. So that means EFGH is the image of ABCD under a reflection over the x-axis. Okay. Well, we learned in section 4.1 that if I reflect over the x-axis, in general, I can take the y value and change the sign on it. Okay, so the first thing I'm going to do is get the coordinates of ABCD, which I've listed over here. Okay, and then what I'm going to do is I'm going to take each of those coordinates and switch the y value, because remember now when I reflect it over the x-axis, it's going to come down here. Okay, it didn't even ask. We didn't even ask you to graph it. It just said come up with those coordinates. So it's going to end up down here primarily in the fourth quadrant, with D being over here in the third quadrant. So I'm just going to take all of my y values and switch them, except for, of course, C, which is on the line of reflection, so it's going to remain there. So my final answer would be these values. So I've just switched each of the y values.